Log on, tune in, find out. Another good idea from Cambridge.
Plamen Stefanov from Purdue University. Well, I believe we'll talk about the similar theme as Alexander Wolfgang, the identification problem in SPECT. So please, Plamen.
Okay. Thank you. So I'd like to thank the organizers for organizing this nice workshop and the whole program, and for arranging this nice weather outside. I'm not joking, this is much better weather than yesterday. And I wanted to take the opportunity to advertise this conference in honor of Günther Ullmann, 60th birthday next summer in Irvine. So you can find more details here on my webpage, or you can just Google it. Okay, so the title of my talk is the mathematics actually of the identification problem. I'm going to explain that problem in a moment. So I'm going to present uniqueness results, non-uniqueness results, and stability results. And this is related to Bookham's talk, but I'm going to explain in what way in a moment. Actually, this is this part of his talk that he didn't have time to present. It's related to that part. Okay, so this problem arises in SPECT. SPECT is single photon electron computing tomography, I think. So what we do, we have a patient that takes some radioactive substance, and we measure the radiation which is emitted by radioactive markers inside the body, and that is modeled by function f of x, which is a source function. So here is a rough picture. So this is the patient, and then we have source inside, well, isotropic in that case. And you want to measure the radiation at the boundary of that domain outside of the body, but there is attenuation, A of x. And that attenuation is significant enough to be a problem. And actually what we really measure is attenuated signal. You don't measure this with the full strength. There is some loss along that ray. Okay, so the question is, can we recover F, which is what we really want to know. But we don't know not only F, but we don't know A either. A is the attenuation again. So the question is, can we recover both? But we don't really want to recover both. We just want to recover F really. But if you can recover both, then it will be even better. I mean, that will help you to recover F. So you know F if you recover both. So here's the mathematical model. Well known, this is so-called attenuated X-ray transform. If A is 0, this is just the X-ray transform. I studied that in the plane. Well, it's an interesting question, can I get more information in higher dimensions? If A is 0, is basically the same thing, but if A is not 0, actually this is not a trivial question, but I'm not going to talk about this. So right now everything is in the plane. And B is the so-called beam transform. Usually it's noted by dA, but I reserve D for different purposes. And the identification problem is, given XAF, this attenuated X-ray transform, you want to recover A and F, if you can. Okay. So there is a hidden transport equation that we saw in the talk by Alexander Buchem. So this is a transport operator. Everything is in the phase space. And then we have U, which is function of x and theta, equals f of x. F is that source, this is attenuation. And then you have a condition that says that there's 0 incoming flux. In other words, the only thing that you measure is due to the source. There's nothing that is going to the domain. And what we measure U on, for points in direction that point outside. So this is related to the talk that we saw, but this is actually there is again nothing coming from outside, so this is not exactly what he talked about, and this is related to that part of Buchem's talk that he didn't have time to present. I'm going to mention in a moment. Okay, so now I'm going to present the result in a very short way for those of you that are not going to follow me till the end of my talk. So can we recover both? Well, the short answer, it depends. That I'm going to explain this, of course. Sometimes we can, sometimes we cannot. And when we can, I'm not going to say that every time we can do it, we can do it in a stable way, but you can do it even in a stable way under some conditions. And I think, at least for me, the most important thing that there is a hidden dynamical system in the phase space which is behind this problem. That is not obvious at all, because it looks like almost like some elliptic problem, because it's the integral geometry problem. I'm going to explain in a moment where ellipticity comes from, but actually there is no ellipticity here. There is really a dynamical system. There is Hamiltonian system, and there is some natural flow. And generally speaking, the main result is that if the perturbation of detonation, I mean, you just study local problem, is supported in a set which is non-trapping with respect to that flow that I'm going to explain, then this is a well-posed problem. Okay, if you have the trapping case, then it may not be well-posed. Of course, it's not really if and only if condition, but I'm going to present examples, radio examples, where actually you have a trapping case and you have huge non-uniqueness. So this is ill-posed problem in that sense, not in the sense of stability, but in the sense that you don't have enough data. Okay, so if you know detonation, then the problem is basically solved. It is well known that in that case actually you have explicit formula to recover F. If A is known, and the first such formula appears in this work as far as I know, and then there is another, maybe a little bit more explicit formula by Novikov. There is a version by Natterer. And so the reason that, okay, since we can do that if we know A, we can recover F, this is so tempting first naively to say, okay, let's recover A first, because if you know A, everything is, we know what to do. I think this is the wrong way to look at the problem. I mean, it's a system. You have to recover them both. It will be too naive to recover A first, and then we know what to do. And there are many numerical attempts to do this. And most of what they do is they start with A0, for example, and they look at the picture. They're not completely happy with the pictures, and then try to change A in some intelligent way, because they don't really know what it is. And this is called termination correction, and then get better pictures and so on. So in clinical applications, what people do is actually they try to reconstruct A first. And mathematically this is very easy, but it's a different problem. You have to take more measurements. That actually means you put here a source, and you take additional X-rays, a lot of them, then you recover detonation by simple X-ray transform, and then if you know A, everything is clear. Okay, but it's important problem to reduce those additional X-rays or eliminate them, because this means more radiation, more expensive machines, and so on. And it's also a beautiful problem if you don't have A. What happens? Okay, so here is a picture that I got from the web. And this is actual clinical image, so of heart, I think. Yeah. This is reconstruction if you assume that A is 0. You don't know what A is, you just assume it's 0, so why not? And this is the image that we get. Of course, how you get that image is a different story, because your data may not be even in the image of the operator when A is 0, right? But applied people, of course, this cannot scare them. They'll produce some image anyway. So this is the image with the wrong A. And this is the image with A which is close to the actual one, somehow approximated. So you see some differences here. For example, this is almost absent from those images. So it makes sense to try to have the right A, of course. And here's a machine that they actually use. This is SPECT CT scanner. And this is the device that measures the SPECT signal. So I mean, only those two things. There's symmetry because this is also used for different methods, PET, where you have symmetric particles. And everything else that you see is just to measure A. And this is only CT scanner. So if you, roughly speaking, subtract those two pictures, then you're going to get that. I was looking for image on the web only of scanner that can measure only SPECT, but I couldn't find it. But only those devices are really important for SPECT. Okay, but we don't know the detonation, so let's see what we can do. There's not much progress in the understanding of this problem so far, but there is some still. so there's a related problem if the tunation is constant. Well, it has to be constant in some domain, really, and then you make measurements on the boundary of that domain. And this problem can be studied by Solomon and Hartley, and basically the result is that there's some non-uniqueness. Radial f, and again a is constant, really. But this is not exactly the same problem. I don't want to go into details, but it's formulated in a slightly different way. The tunation is 0, somewhere here is positive there and actually negative there. So it's a little bit different problem, but it's related. And the identification problem with finite sum of delta sources can be studied by Natterer and Jan Baumann. But I mean, it's clear that we have some kind of discrete information. Actually, it's not really discrete, but it's like random transfer with discrete number of centers or points. So it cannot have uniqueness, but still Natterer showed some nice reconstruction, some nice pictures. Oops. I mean, another point of view of this is a range characterization problem. So you think of this operator with the tunated transform, you think about the range. And if the range happen to be the same, you cannot have uniqueness because, well, that's quite clear. If they intersect only the origin, that actually means that you can have uniqueness. But those are two extreme cases, of course. Either they not intersect except the origin, or they're the same. But still, range conditions is one possible way to get some information. And numerically, that was used by Bronnikov. And there's a recent paper by Guillaume Bau and Jolivet about some theoretical result based on range conditions, but there are not really uniqueness results there about this problem. So they're related, but not directly. And there are many numerical reconstructions, some of them based on range conditions, some of them just by some other way. And here you just see very few of the people that try to do that. Okay, and then there's this paper by Alexander Buchheim, that the one that he didn't present. This is a recovery algorithm if A priori is known to be a constant multiple of characteristic function of a star-shaped domain. So you have a constant that we need to recover and some interior boundary. And he uses complex analysis. Okay, so the main question that we study the following. I mean, probably I don't have to show this slide to this audience, but I included this nevertheless. So interested in uniqueness for those pairs, interested stability. So what we get is Hölder stability under some conditions, which is more or less the best we can get. Well, the best is Lipschitz, but this is almost as good. And some kind of reconstruction maybe, but well, we don't get to reconstruction, but we show how we can get a Fredholm problem out of it after we linearize. So I'm going to go quickly over that slide because this audience is well familiar very well with the theory of inverse problems in principle. Okay, so we linearize our operator. I mean, it's linear with respect to f first, clearly, but it's non-linear with respect to the tunation. So this is notation that we use. W is a weight on the phase space. And then it turns out that the linearization looks like this. I mean, use this symbol delta means like Frechet derivative, roughly speaking, but I mean, this is by how much x changes if you have small changes of increments of a and f. And what we get is the following. We get a sum of two X-ray transforms. Okay, one of them is the original one, and this is, of course, there's nothing mysterious about that. It's a linear problem with respect to f anyway, so we have two f's, we just subtract them, okay? So this is quite clear. And this is actually that needs some work to compute. So it turns out to be operator which is of the same type. So it is X-ray transform of delta A, which is the difference of two A's, roughly speaking, with a weight that looks like this. Okay, so you see f, this is the background f that is fixed, is involved in basically some integral of f from point and direction until we get to the boundary or outside of the support, but it's actually attenuated integral. And this is another way to write that weight. in terms of solving the transport equation. And see that even if, okay, for example, if A is 0, of course those two are the same, with that negative sign here, of course. So this is just two different ways to write this. I mean, my advice will be for this talk just to think that the background A is 0 and try to see what happens there, because that A is not really so important to understand what is going on. So this is the weights in the phase space. From here, point and direction, just integrate U with the attenuation to go to infinity. Not integrate U, integrate F, sorry. F is the background F, right? You linearize near some fixed A and F. Oh.
Did you just linearize around the attenuation?
Well, linearize, I think of this as a pair, so linearize with respect to both. But it's already linear with respect to F, so there's not much to do here. I mean, if you just linearize with respect to A, you're only going to get this term. And the other term is just automatically. Okay, so in other words, the linearization looks like this, with the weights. I mean, the original X is just of this kind, which is a special weight. And if you look at those two weights, there's a term that is repeated here, this exponential, which is elliptic. So from Michael Walker point of view, it doesn't really matter. So you basically have minus U and 1 here. This is the way to think about it. Okay, so now the new problem is to invert a sum of two weighted X8 transforms. Right? So you have two functions, two weights. Of course, if the weights is 0, you cannot do anything, so there should be conditions on the weights. But right now, you have two arbitrary weights in the phase space, and you want to invert this transform. Well, we have enough trouble with one transform. Now we have two, the sum of two. And the first impression that this is too much to ask for. Just two functions is too much. But then look at this and see that you actually have, if you think microlocally, what we can get from integral over one line. I mean, from one line you cannot get much, of course, but if you have a line, a neighborhood of a line, what we get those conormal singularities, which are perpendicular to that. Okay, but now you can integrate in this direction, then in this direction, and still recover the same singularities. You don't recover them all, but you still get information about those singularities. So for any such line, actually, you have really two equations, in this direction and in this direction. And the weights in principle differ if you change the direction, and they're in the phase space. Okay, so we have a system, roughly speaking, 2 by 2, and if some determinant is now 0, then we might be able to solve it at least microlocally. Okay, on the other hand, this determinant turns out to be always 0, but always I mean the following. For any x, there is a direction where the determinant will be 0. We'll see that in a moment. So the initial idea is just to find condition that will make this elliptic fails over any domain in the X space. We'll see this in a moment. Okay, so to study this operator, we take the Fourier transform over a plane which is perpendicular. Actually, it's not a plane, really. This is two-dimensional. This is a line perpendicular to this line. This is one of the usual tricks. And then you get this differential equation. The W1 is just the weight. You put this thing there. You choose one possible way to rotate perpendicularly. Just you have to fix the orientation here. Okay, and but you get plus and minus. I mean, that is related to the fact that you can integrate this in this and that direction, or another way to think about this, you get this and the opposite singularity. You actually get two equations really, with plus and minus. So this is 2 by 2 system of 6 differential equations, and it's necessary to look at the determinant. Okay, so the determinant, I prefer to work in the tangent space, and then at the last moment to replace theta by this expression here to go to the cotangent bundle. I mean, look at this determinant here, and then you replace theta by this expression. In other words, you just rotate theta by 90 degrees. And if that is non-zero, then this is elliptic. Well, on the other hand, this is odd with respect to theta. This is just the odd part, more or less, of this expression, right? So there is no way that it can be elliptic for any fixed x and for all theta. So if you fix x, there are at least two states where this is 0, maybe even more. So ellipticity is lost, so there's no hope that you can use that argument. Okay, and then there's a characteristic variety. And let's study that characteristic variety. Characteristic variety where this is 0. But again, it's very convenient to think about the set where W is 0 in the tangent bundle, and then the last moment to replace theta by that. This is somehow easier because when you want to relate this to the geometry of the problem. Okay, so I said that before that you don't have ellipticity, you surely have a lot of zeros, and you should study the Hamiltonian floor related to P0. And let's for a moment consider X-ray transform, just single X-ray transform, not sum of two, just the classical problem, but we have a weight which is non-trivial, non-vanishing. Then you can recover those singularities which is normal to each line if you just know integrals in some neighborhood of that line. I mean, that is well known. But the fact that you can do it is the following. You can study this operator, prime means transpose. It's elliptic differential operator, and it's elliptic because you assume that the weight is not 0. Otherwise, it will not be, in principle. In other words, that ellipticity comes from this assumption, of course. And this has the usual consequences. You can recover the singularities, you get Fresholm problem, finite dimensional kernel, stability if you have uniqueness, and so on. By the way, you don't always have uniqueness, and there is actually more than one very nice example by Jan Baumann that if the weight is positive, but not of special type, actually you have examples where the uniqueness is lost. But the ellipticity is always there if the weight is not 0. Okay, going back to I, this I clearly means sum of two X-ray transform, remember? I mean, this operator is never elliptic over any domain, as I explained, and it has a characteristic variety. So let's just study those back characteristics and see what happens. So we call the projections of the back characteristics of the X space rays, similar to what we do for the wave equation, but of course there's no wave equation here. Okay, and all this will not be very useful if the Hamiltonian field vanishes on some open set. I mean, then all those Hernandez theorems, of course, they apply, but they give you trivial consequences. If, let's say, P is 0 everywhere, the theorem is true, but doesn't tell anything. Okay, so this is one of the conditions that tells that you can get some non-trivial result by propagation of singularity, and this actually means that the Hamiltonian field is non-radial. So in other words, this is the least condition that you should require to get some meaningful result out of this flow. Okay, so this is equivalent to the following conditions about the weight, the determinant, and they're in some sense pretty mild. I'm going to relate them to the actual problem later. Okay, if you want the rays to be smooth curved, then you want to impose a stronger condition, but you don't really need them to be smooth curves projected on the X space. Okay, and here's an example, radial example. So far this is example of the inverting of sum of two X-ray transforms, right? I mean, I'm going to connect it to the attenuation problem later. So this is an artificial example in that sense that it is not coming from the identification problem, but it has the advantages to simple. Okay, so you choose those two weights like this, and then you can, and actually it's connected to the attenuation problem, but it's some simple version of that. Okay, so you have those two weights, and then you compute that determinant. It turns out to be that you replace theta by xc perpendicular basically, and you get this symbol. And this is the symbol of the operator of rotation. Yeah, okay, it's actually different. Yes. Okay, just oh yes, thank you. So this should be 1, yes. So this is derivative with respect to the polar angle. Okay, and the back characteristics are then the phase space, of course. They're those circles, roughly speaking. But so-called rays, I'm going to show a better picture in a moment, all circles with radius with center 0, including the origin. Origin is a degenerate array as well. But if you go into the phase space, of course, you have to think about normals to that. If you just look at what we have here. So in other words, by characteristics, x moves along those circles, and c is always perpendicular to them. Okay, and actually you can analyze this transform with those waves directly. You can use Fourier transform, you can just solve it right away. You don't need any microlocal analysis for that. But what is interesting to connect microlocal picture with what we can get directly. So this is the kernel of this transform. You see, you can recover the second component, but not the first one. The first one in the kernel has to be radial. So you cannot recover those singularities that are characteristic, but not only you cannot recover those radial singularities for G1, you cannot recover anything radial, so it can be any radial function actually. But you can recover the second one. Okay, this 0 shouldn't be much surprise, so you cannot get all the information about one system just based on the determinant. Of course, you have to go back to study the actual matrix, the rank when the determinant is 0, right? Okay, so there's the infinite dimensional kernel in that case, and the level set, the race appears level set of the function that kernel. So you see that this is an example where ellipticity fails and you have huge kernel. Okay, so let's go back to the idea to study the Hamiltonian flow. So you apply the theory of C differential operators of real principal type. I mean, this is a matrix valued operator, but you can always multiply by some matrix to make the principal symbol scalar. You don't get system which is equivalent to that, but you get system that you can analyze and give a lot of results. And okay, so propagation of singularities theorem tells you the following: if there is one singularity, one by characteristic, then all points consist of singularities. But if you a priori know that the support of G is in some set, which is non-trapping, so all by characteristic eventually leave. Since they leave, I mean, this is, think of this as in the phase space, but then you project it to the x space. So if all by characteristic eventually leaves, f is G actually, is 0 here, so there are no singularities here. There shouldn't be singularity inside. Yeah, this is a very old idea, actually, it comes from the 70s and the work of Heuermander and Dustermant. So we call K not trapping with respect to the Hamiltonian flow if there is no complete by characteristic over K. Over means the following: so K is in the x space, meaning you work in the phase space, then you project, and you still want all by characteristic to leave eventually. I'm going to show you examples later. Okay, so if a priori you know that the support of G is in a non-trapping set, that actually you can recover the singularities by the argument that I presented. Actually, you can do it better. You can say what kind of regularity you gain. And if you're careful, you're going to notice here that there's a loss of one derivative. So this operator, at least each component, is sum of two operators order minus 1/2. So you'd expect here to get s minus 1/2. But we get s minus 1/2 minus 1. So there's a loss here, but that loss is related to this. If you actually want to constructively recover the function, you have to start integrating from somewhere it is 0. And when you integrate, you gain regularity here, but you don't gain regularity there. Right? So this is where the loss comes from. Okay, and here's an example. I'm going back to this artificial radial example. This is a non-trapping set. No complete circle belongs to that set, and this is an example of trapping set. Right? So in the first case, if you want to invert this operator, this is a well-posed problem under the a priori assumption that everything is supported here, and here it is not. And actually, you can get this from the actual solution that I presented. You have a lot of radial functions in the kernel, and if k is like this, of course, you can find radial functions that are supported here. No radial function can be supported here, so the kernel here is actually empty. Okay, so now back to the actual problem, the identification problem. So if you look at the linearization of this operator, what is the role of W? Remember, there was an important function W there, and you just replace this by I mean, this is not so important. Just rotate basically theta, and then you get your Hamiltonian. So W is 0. When this happens, okay, why? I mean, you really have to go back, and I told that you had ways of this kind. And there was a negative sign here, and there is U. So this is W1, this is W2 in the linearization identification problem that I really want to study. I mean, this is elliptic, doesn't really matter. So you basically have minus U and 1. This is W1, this is W2. If you take the determinant, you just get, and take the odd part, you just get the difference of those two. This explains that expression. This is basically W in the problem that we really want to solve. And looking for X and theta such that this is true, in other words, W is 0. And here's the picture. So you at point X, you choose different directions. You're looking for directions so that we integrate F in this direction. In the opposite one, you get the same things. We'll integrate with the tunation, but let's forget about the tunation. Also, you get characteristic X and theta only if that integral is equal to that integral of F. Okay, and then you go to different point, you compute that field again, and this green line looks like a ray, right, roughly speaking. Okay, so now what are the main results for the linearized map? So first, this is the major assumption here. You assume that they are supported a priori a non-compact, non-trapping compact set with respect to the flow. Then you can recover the singularity with loss of one derivative, as I explained. The kernel is finite dimensional smooth. And just follows from ellipticity. Actually, it's a hyperelliptic really with the loss of one derivative, but still has the same property. Okay, and if you know that it's injective, which is, I'm going to talk about this in a moment, but if you somehow can prove in different ways it's injective, that should get a stability estimate. Again, there's a loss of one derivative. It should be plus 1/2, but it's 3/2. I mean, not that it should be, but you expect it to be, but it's not. And now, this is a delicate part here. What you want to perturb a little bit A and F, those A and F here. Well, this is preserved, but you need a little bit stronger condition. You want K to be pseudo-convex, and this is not the same pseudo-convexity as in the Kahneman estimates. It's a different one. And here's the definition with small letters. Hopefully nobody will try to read it, but let's say it's a little bit more general than non-trapping. And actually, I try to construct examples that are related to this, which non-trapping, that not pseudo-convex, I couldn't. So, I mean, apparently they exist as abstract examples, but I try to construct actually example related to this problem. That doesn't mean it doesn't exist, of course. Okay, let's just say this is slightly stronger than non-trapping. Okay, what are the conditions that can imply injectivity? I mean, this is much more delicate, because everything else is just micro-local, and injectivity is usually a more delicate question. Okay, so one condition is a local condition. You're at some point x 0, such that if that w is 0, which is the major function, fundamental function determinant, when you change the angle a little bit, it's not 0. This is a simple 0 with respect to the angle. So let me explain. Okay, so you have x0 here, and this is the support of f. And let's say that you found theta such that this integral with the attenuation and this integral are equal. Okay, then you change the angle a little bit, and you still compute this and this integral, and you want them to really change. In other words, the derivative to be non-zero when you rotate theta. So if you have this condition, then in some small neighborhood of that point, if you assume actually that a priori the support of delta A and delta F are there, it is injective. Okay, so why? I mean, this goes back to very old ideas. I mean, you have this estimate here, and if you assume that the support is small enough, actually you can. So if you have function that is very smooth and you have very small set, the integral over that set will decrease. If you a priori know it's very smooth. If you don't know that, of course, the function may have integral 1. But if you know a priori smooth, the integral will decrease. So those are ideas that go back actually quite old. And they're used in the local solvability of some PDEs. Okay. Another condition for injectivity, if BA, remember this is the bin transform of A and U analytic in K in your set. If you just assume that A and F analytic, well, that's even better, but they have to have compact support. But this is actually a weaker condition, which is better. So what you really want is you start integrating from here in all directions, and you want to get analytic function. So if it jumps here across some surfaces, this will not change the analyticity. Of course, it will change it if you go too far from this point. Right? Okay, now I just formulated the results so that I can connect it directly to the abstract problem of inverting two X-ray transforms. But if you study this particular one of the weights is elliptic, which is applied to F. The other one might not be elliptic. So we really don't have problem to recover delta F, at least microlocally. You only may have problem to recover delta A, because you may lose ellipticity here. So the actual condition is you want the support of the perturbation of the attenuation to be in a priori non-trapping set. There's no condition for F really, for delta F. Okay, now results about the nonlinear map, which is the actual problem that we want to study. So here the local uniqueness and stability theorem. So you fix A0 and F0, which is your background A0, F0. And then you want the perturbations that you used to call delta A and delta F so far. You want them to be supported in a set that you a priori know is pseudo-convex. Remember, it's slightly stronger than non-trapping with respect to A0 and F0, of course, with respect to Hamiltonian flow related to that. Okay, second condition, you want local injectivity of the derivative, roughly speaking. It's like implicit function theorem. And third condition, I mean, everything here is local, near A0 and F0. This is actually a weaker condition, which is better than removing B here and putting F there, right? This is actually more general condition in some sense. But it just tells you that this is small and this is small, in certain sense. Okay, then for small enough epsilon, you have injectivity. Okay. And also there's Hölder stability. I didn't formulate this estimate here, but you have the typical conditional Hölder stability estimate. Okay, this is what I mentioned before. This condition is just smallness condition for those differences. It's actually a weaker condition, which is good. And a presenting condition for injectivity before, right? But this is a theorem that says that if you can prove injectivity for some other class, okay, then automatically you can apply this. Okay, so this is the main result about uniqueness and stability. And of course, the crucial condition here is the pseudo-convexity, in other words, the non-trapping condition. Okay, and here's a radial example. Now this is actually a real example. So this is actually a attenuation problem. Before it was artificial one. So you study the linearization near attenuation 0, and probably that is the most interesting case. If the attenuation is too large, what you measure is very small, and probably there's not much hope you can do much. And F is just characteristic function of the unit ball. And you linearize near those A and F, and of course you get that, as I mentioned before. 1 means weight 1, this is just the standard random transform, and W looks like this. It looks bad, but if you compute this determinant W, remember you have to take the odd part of this. Actually, this doesn't matter, and you get this expression. This is exactly the same expression up to that factor here that we got in that artificial example before. So the Hamiltonian flow is the same. All those rays are still all those concentric circles. And as before, non-trapping and trapping means you have or you don't have complete circles in K. And here is absolutely the same picture that we saw before, because the Hamiltonian flow is the same. So this is non-trapping, and also pseudo-convex, very easy to see. And small enough perturbation which is supported here are recoverable. I mean, clearly we have an elasticity here, don't have to check it, it's obvious. And but the other remark that I made, actually you only need pseudo-convexity or non-trapping for perturbation of A, really, not for F. So what does it tell for practical terms? Okay, if you linearize near this pair, in cases like this, locally you can recover F and A. Here, you may not be able to, and actually in a moment I'm going to show that you really don't recover them. Okay, so in the whole ball, which is of course trapping, you can analyze the kernel, and it's very easy. So you analyze the kernel, you're looking for, you get that the kernel must consist of radial functions only. You prove that. And then you show that they have to be related like this. So this is the usual random transform notation, but again, those two functions are actually one-dimensional really, because they're radial. So this is one-dimensional equation. You can analyze it. You can show that if delta A is given, you can actually solve it for delta F. I mean, it's a little bit tricky because you have to make sure that you're in the range of the random transform. But this is random transform radial function, so very easy to analyze. So actually, there's a huge kernel, which is described by this equation. You don't really have uniqueness for the linearization, no matter what to do. Okay, so what happens if you consider the nonlinear problem? Okay, so this is theorem. So take F radial and C0 infinity, and then the linearization has infinite dimensional kernel, which I explained actually just the previous slide. But what is more interesting is actually the nonlinear problem, of course. And here is the result. So if you take A and F radial and smooth, you can always find F0 such that this is true here with attenuation 0. So in other words, A and F and 0 and F0, and F0 you can compute, they have the same data, so you cannot distinguish between them. Of course they can...
Vice versa. Vice versa, 0 and 0, there is A.
Okay, let's see. Okay, so if this is given,
Yes.
you can find F0 that depends on those two, such that this pair has the same data as this pair.
Vice versa.
Vice versa. Okay, so if you have this given, well, I'm not sure about that vice versa, because in order to do that, I solve some other type of equation with 0A. So this relatively simple equation is actually showed the previous slide. You can invert it directly. And in order to show what we're asking, I have to solve the equation with A, which is more complicated, and I don't know how to solve it. I don't even know how to characterize the range. Actually, this is another project. It probably can be done, because there is a characterization, some kind of characterization here. But I didn't want to go into this detail, because for me it is important to show that if non-trapping condition fails, there might be infinite dimensional kernel. I don't want to describe the whole kernel, just to show that bad things can happen. Okay, this is the last slide. And you can write explicit formula to compute F0 if you know A and F. And okay, again, this shows that non-trapping condition is important. So I'm not saying it's if and only if, but at least in that case, if it's trapping, then you lose uniqueness with infinite dimensional kernel. Okay, that's the end of my talk.
Thank you very much for the interesting talk. So, questions?
Can I ask if you know anything about PET? Because I'm guessing this doesn't work for PET because it's simultaneously theta and minus theta.
Okay, that's another thing that I'm going to look at. I tried to do some calculations, and it turned out that it's actually different. So my preliminary calculations show that those two equations that I mentioned, that they give you system 2 by 2, for PET, they might be equivalent actually. So I'm afraid that for PET you have less. For PET you may have less information. It may be more useful than this one, but I didn't do much about it.
Okay, so if no other questions, then let's continue with the next speaker right away. Thanks.